Okay, hi everybody. What I'm going to do in this video is talk some more about Bose Einstein statistics, in particular particles with mass. And we're going to do that by first going back and reviewing how we get the degeneracy for quantum systems with mass. So we're going to go back and talk about that. Then we're going to get back to the Bose Einstein formulation and talk about normalizing a gas of bosons that's getting very, very cold, very close to T equals 0 on the Kelvin scale. So that's where we're going. Okay, so let's get back to finding the degeneracy then for a quantum system. So when we're talking about a quantum system, we're talking really, for now, we were talking about the particle in the box. So we got a three-dimensional box where the sides are basically infinitely high, meaning whatever particles we have in the box are contained in the box. They cannot leave. And we found that the energy of the particles in such a box are equal to some constant stuff, and then it depended on these quantum numbers, nx, we called them, ny, and nz. So that was our energy. So if we're talking about the number of ways that you can have a specific energy, you could have, for example, nx is 1 and y and nz is 2, or you can have nx is 2, nz is 2, and y is 1. There are a number of ways, permutations, that you can have and get the same energy. So let's draw a coordinate system, and let's label this nx again, ny, nz. Now, you can only have discrete integer values of these things. But for fairly large energies, they don't really look discrete. They look almost continuous. Sorry, my camera went out there. So here's my coordinate system, nx, ny, and z. And the number of different states that you can have a certain energy would equal, let's say we take, let's call r squared, let's just call it, equals nx squared plus ny squared plus nz squared, where r is our radius of a sphere. So this is supposed to be a sphere, but we can only have positive values for our n's. So it's really 1/8 of a sphere. Here's a wall there, there's a wall there, there's a wall there. So the number of states that are contained within this 1/8 of a sphere is equal to 4/3 pi times r radius squared. R radius cubed, I'm sorry. It's a volume here. And then we only have 1/8 of that. So that's the number of states that are contained within that 1/8 of a sphere. Now, the degeneracy is how the number of states change with energy. So one way to write that is this, a derivative. So how the number of states change with energy. That's another way to describe the degeneracy. So if I take a derivative of what I have here, now I'm going to rewrite this. E equals, I have up here E naught, but if you remember, E naught was, for a particle in a three-dimensional box, is h squared over 8, the mass of the particles, L squared, where L is the length of the box. We're assuming it's a cubic box. So that would be E naught. Then we have our nx squared plus ny squared plus nz squared. So if you go back and look at the particle in the three-dimensional box, that's what we had. So now I can write that as r squared here instead of nx, ny, and nz all squared. So r is equal to the square root of e over the square root of this stuff, which is e naught. Okay. Now, what that's going to do for me is I'm going to write n as 1/8 times 4/3 pi, and now instead of r I can use this, and then I cube it, so I'm going to get e to the 3/2 on top over e naught to the 3/2 on the bottom. Now I take the derivative with respect to the energy to get my degeneracy. So first of all, the 4/8 is just 2, and then I have a 6 here, so I have a pi over 6. I'm still going to have the e naught to the 3/2 because I'm taking the derivative with respect to e. And then when I do that, I'm going to get a 3/2 and e to the 3/2 minus 1. So I'm going to get e to the 1/2 on top. So that's the same as pi over 4 e to the 1/2 over e naught to the 3/2. That's my degeneracy. Now, if I put in the fact that, so e naught was h squared over 8ml squared, e naught to the 3/2 then would be h squared to the 3/2, so that's going to be an h cubed on top. On the bottom, I'm going to have 8m to the 3/2. L squared to the 3/2 is going to be L cubed, which is the volume. Okay? So that's h cubed over the volume. And by the way, 8 can be written as 2 squared times 2. So what I'm going to get is 2 cubed times 2m to the 3/2. Getting kind of small there, but that's what I'm going to get down there. So I'm going to get now my degeneracy. Let's move this up. My degeneracy is equal to my pi over 4 e to the 1/2, and then e naught to the 3/2 is this, h cubed over 8 2m to the 3/2 times the volume. And of course I can flip that up, so that's going to be pi. Then I'm going to have my 8, my 2m to the 3/2, my volume e to the 1/2 over 4h cubed, and of course that 8 over 4 is just going to become a 2 on top. Okay. So we have 2 pi 2m to the 3/2 e to the 1/2 times the volume up here over h cubed. That is our degeneracy. So now we're going to, go back, and we're going to rewrite our Bose Einstein total distribution now. This is number of particles with energy between E and E plus delta E. So now for us that's going to be 2 pi. I'm going to put the volume here, 2m to the 3/2 e to the 1/2 dE over h cubed, and then I have e to the alpha, e to the e over k KT, and then minus 1. So next we want to talk about normalizing this. To gain some insight on what's going to go on, we want to normalize this now. What I'm going to do is the trick I did before, where I'm going to let x equal E over the Boltzmann's constant times the temperature. So that, again, that means E is going to be replaced with x times KT. So when I do that, I'm going to get, and I'm also, by the way, I'm going to divide by the volume here. So where V is going to be equal to my 2 pi, my 2m. And now, because I'm going to replace E with x kt, and I'll have it to the half power here, but I'm going to have it to the first power here when I put it in for E here. So I'm going to get a kt to the 3/2, and I'm going to put that in the brackets here. Okay. And now I have x to the 1/2 dx over e to the alpha e to the x minus 1. Now if I integrate that over all possible energies, 0 to infinity, then this becomes just n over v. So we know what we can do here. We actually know what the maximum value for this integral will be if I pull out all the constant stuff. I have 2 pi 2m kt to the 3/2 square root of x dx e to the alpha e to the x minus 1. I know the biggest that integral can be. Let's see here. So I know the biggest this integral can be is when e to the alpha is equal to 1, and this will become and I think we've done that already. It comes 2.32 or 2.315 if you go to 4 significant figures. So what we have is the number of particles per volume has to be less than or equal to this 2 pi 2m kt to the 3/2. I think I'm missing an h cubed down here. Over h cubed times 2.315. So what it tells you is we have this relation. Let's say let's rewrite it. Let's solve for the temperature. If I solve for the temperature, I would get that the temperature is going to have to be greater than or equal to, I'm leaving the temperature over here and taking everything else to the other side of the equation. It'll turn out to be h squared over 2 mass times Boltzmann's constant, this stuff, and over v, and my 2 pi times 2.315 will be there, and that'll be to the 2/3 power. So that's what I'll end up with. Now, the temperature has to be greater than or equal to this side, because remember this 2.315 came from we made the integration as big as it could possibly be. And in here we have all constant stuff. If we assume that our number of particles per unit volume is constant, but we're going to get down to a lower temperature at some point, this expression is not going to be able to be satisfied when we go down to a low enough temperature. So we have T is greater than or equal to this. If we make T equal, so we go down as low as we can in temperature, we're going to call that the critical temperature. Now, let's calculate the critical temperature for something, and then we'll talk about what that means. So let's calculate, or let's try to at least estimate the critical temperature for helium. And helium isotope 4 is the most abundant isotope, so we'll look at helium-4. It just means we have two neutrons and 2 protons. All right. I don't know what the number density is for helium-4 at very low temperatures. So here's what I'm going to do, since this is an estimate. I'm going to assume that the number density is on the order of 10 to the 28th particles per meter cubed. Now the reason I chose that is that's roughly the density of a solid, so I'm assuming it's getting close to that at very low temperatures. Again, it's just an approximation, just to do a back of the envelope calculation. So T of C is going to equal, I need Planck's constant, 10 to the negative 34 joules seconds, and I need to square that over twice the mass, and the mass will be 4 times the mass of a proton, which is about this, kilograms. And then I need Boltzmann's constant, which is 1.38 times 10 to the negative 23, and I think it's joules per Kelvin. And then I need my number density over 2 pi times 2.315, and I got to take this to the 2/3 power. So when I stick that into my calculator, what I get is about 1.9 K. So the critical density, or critical temperature, I'm sorry, is about 1.9 K. Now that's off by quite a bit. It turns out if you want to call it the accepted value, the experimental value, 5.2 K. But you remember I was just really roughly estimating the number density. Okay, so once you reach this critical temperature, what happens? So when T is less than or equal to the critical temperature, what happens? Well, what happens is you cannot satisfy the equation we had up here at the start, which means you can't normalize the system. So you can't normalize the collection of gas or the system. So why not? What's going on? Well, keep in mind, things are, as you get colder and colder, are going to try to go to lower and lower energies. So at some point, you're going to be significantly populating the ground state. And for bosons, there's no Pauli exclusion principle. We can't say you cannot populate the ground state. So you're going to significantly populate the ground state, and we're not really accounting for that. Okay? So how could we account for that? Well, we go back to N equals 2 pi times the volume, h cubed, 2m kt to the 3/2, 0 to infinity. square root of x. Now I'm going to keep the alpha in here, and e to the alpha times e to the x is e to the alpha plus x minus 1 dx. Okay? Now, if that's not taking into the ground state, I'm going to add on a term that takes into account the ground state. But you expect this to be populated more and more as the temperature goes down. So we'd like to know how that might depend on temperature. Okay, so I'm going to rewrite this again. I'm going to do well, I'm going to rewrite it again. I'm going to write it like this. It's going to look very much the same. I'm going to pull out the t to the 3/2, and I'm going to pull out the e alpha from the integrand down there. And then the integral becomes this. Okay, so all I did was write the integral as and we say that's going to be okay. Now, I wrote it like that for a reason. We'll come back to that up there. I want to get an estimate. I actually would like to know how does the number in the ground state depend on temperature? So that's my question right now. I want to see if I can explore that a little bit. So let's think about just the ground state. So we're not going to do an integration. First of all, we're going to assume the energy of the ground state. So we'll call it E sub 0. Let's assume it's 0. Okay. What else? So now if we want to calculate the number in the ground state, we don't do an integration because there's only one energy. We would just have the degeneracy of the ground state times the Bose Einstein function evaluated at the ground state. So that I'm going to assume that there's only one way to get an energy equal to 0. Okay? So I would have this, 1 for that, and then e to the alpha, e to energy equals 0, so I'll put a 0 there, minus 1. So I just get 1 e to the alpha minus 1. Okay, and then again, that should be my number in the ground state. What else? Well, if alpha is small, like as it goes to 0, we could write e to the alpha, expand in a Taylor series, should be 1 plus alpha plus, and you can go on. And if you look at what we just have here, if you look at this and this, and you solve for E alpha, what do you get? You get E alpha is 1 plus 1 over n naught, the way we've done it up there. So if that's equal to 1 plus 1 over n naught, it tells you alpha is approximately goes as 1 over n naught. So as we start populating, it's going to change as we start populating the ground state. Okay. Now I think I'm ready to go back up, way up to here again. Okay, so I'm going to come down here. Now what I'm going to do is I'm going to divide both sides of that equation by n. Oh, I guess what I'm forgetting up here, I rewrote that to here, but I forgot plus the number in the ground state. Okay, so now I'm going to divide both sides by n, so I get 1 on this side equals, n divided by n is 1, equals 2 pi v 2m k 3 halves h cubed n t to the 3 halves, it's there, over E alpha. But E alpha, I'm going to write 1 plus 1 over n naught. Okay, this is E alpha. And then plus O times the 2.315 plus n naught divided by n. Okay. Now, this is what we're working with right now. So again, we just took the top one up here and we divided by n, and the only thing we did is we substituted what we had in here for E alpha. We use this. Okay, and we end up with this. Now, let me move this up. This is the fraction of our particles that are in the ground state, right? N naught is the number of particles in the ground state, and n is our total number of particles. So that ratio is what we have in the ground state. This right here, all of this, if you remember how we defined the critical temperature, that was our definition of the critical temperature. If you go back and you look at this, it turns out, first of all, I'm going to say 1 plus 1 over n naught is approximately 1. And then I'm going to rewrite all this stuff here then as t to the 3 halves over the critical temperature to the 3 halves. So all this other stuff, once you make that 1, you can write as the critical temperature to the 3 halves power, or 1 over the critical temperature to the 3 halves power. That includes you use this too. So then I have this. I'll leave that to you to show that all this stuff, make that 1 is 1 over critical temperature to the 3 halves. So then I end up with this. You remember what I was trying to do was find out how the ground state depended on the temperature, and now I have it. I have the fraction that's filling the ground state as a function of temperature. Well, this is approximate. Okay. So as we get lower and lower in temperature, the fraction that's filling the ground state gets greater and greater. So we'll stop at that point with this result. And next time, then in the next video, we'll talk about the Bose Einstein condensate, which is a collection of atoms where they're all in the ground state. They're all in the same state. You have one big macro quantum state. So we'll talk about that next time.